produce a talk while organizing this whole conference. So I think that's quite an achievement. And he's going to be talking about next paradigm programming languages. What will they look like and what changes will they bring? And I think we're in an appropriately equipped room. So if you disagree with something that Yanis is saying, there's access in the back. There's some swords and an iron over there. So we can make it a bit more interactive. Thank you, Yanis.
Thank you, Thomas. Everyone can hear me okay, right? Okay. Neville, you're charged with bringing me a sword if anyone tries to attack, because I need something to defend myself with. This is an essay, obviously. You will disagree with lots of things I have to say. But obviously, it's also a very popular topic, as we can tell both from attendance here, and also by the fact that when I first wrote this, I wrote it back in May, I think, or April maybe. I just submitted it to Onward, to the Onward essay track, and I uploaded it on Archive, and it got picked up and appeared on Hacker News, and got lots of comments. And the takeaway message here, well, who saw it on Hacker News? So some people saw it on Hacker News. Takeaway is Hacker News, getting your whatever paper, article to appear on Hacker News is a great way to reconnect with old friends. So people who are like now at Apple or Google would email me and say, hey, you're a celebrity. And it's a horrible way to get any kind of feedback because nobody read the actual paper. They just commented based on the title. You know, on Hacker News, you don't even write the summary. It's just a link to the PDF, and people just start writing. And I can tell you, almost nobody actually read the thing. I think I got one meaningful, direct email with good feedback. I got a lot of better feedback from the Onboard Essays Committee. So the wisdom of the crowd is to be questioned sometimes. Anyway, it's a sexy topic. Next paradigm programming languages. We all want them. So what's the excuse for this? It's quotes like this. This comes from a popular blog post that says, we've passed the point of diminishing returns. No future language will give us the factor of 10 advantage that assembler gave us over binary. And that statement you may believe or not. Also, no future language will give us 50% or 20% or even 10% reduction in workload. Now, you all know the no silver bullet essay, perhaps, right? So who knows no silver bullet? Fred Brooks's essay. Even Fred Brooks, who's much more accomplished, did not risk a prediction like that. He never said no future language. He actually said, within the next decade, there's not going to be a language that will give us an order of magnitude improvement in productivity. So this is a pretty bold statement, but we kind of believe it's pessimism, right? We all believe that largely language evolution has mostly run its course. We're probably not going to get order of magnitude improvements. Will doesn't.
I totally disagree.
Excellent, thank you. I also disagree. In the past, though, languages have had great successes. The history of computing is full of revolutions in computer languages. Languages have fueled the computer revolution. And we've gotten lots of recognition for it. Now, there have been 53 Turing Awards, now 54, given. And 16 of them are explicitly given for contributions to languages or compilers. So the computer revolution has a lot of languages ideas. And we have gotten orders of magnitude productivity improvements in the past. We're just not sure whether we're going to get them in the future. Now, the future has lots of potential. There are lots of techniques that could bring about order of magnitude productivity improvements. And they're kind of exotic right now, but that's why we're researching them. There's machine learning, obviously. Both the deeper learning stuff, but also the shallower learning from huge code bases, from huge instances. All sorts of statistical techniques. So I can group this as statistical techniques overall, and at the same time I can group all of a whole other set of techniques as symbolic techniques. So we have anything that you've seen on program synthesis is based effectively on SMT solvers, and it invents pieces of code that you and I sometimes cannot invent. It invents very deep pieces of code for bit manipulation, for instance, that are better than what any programmer has ever produced. So there may be revolutions that are coming soon. I am not here in the business of predicting what's going to be the revolution. I think that if we will have a paradigm shift, it's going to be a proper paradigm shift. And paradigm shift, the original term of the Kuhnian paradigm shift, is that it's going to bring about a different set of terminology. We cannot even fathom what the next paradigm is going to be. I don't even have the terminology to speak about. So I'm not going to tell you what is going to be the next paradigm, but I'm going to try something a little interesting. I'm going to try to predict what I think is unknowable. So I'm going to say whatever is going to be the next paradigm, languages that use statistical techniques, languages that use symbolic techniques, declarative programming, or whatever, without knowing it, I will try to speculate on what are the properties of such languages and programming in such languages that are kind of inevitable. Let's say I have this black box that's magical and it gives me an order of magnitude productivity improvement. What have to be its inevitable properties or its inevitable impact on the software development process? Now, of course, if the paradigm ever shifts, which I'm not 100% sure, sometimes I believe what Will said, sometimes I'm pessimistic. But if the paradigm shifts, what's it going to look like? So, to make this a little concrete, throughout the talk, I'm going to be giving examples from my experience, and my experience is also how I came up with thinking about this. And my experience for the past 10 years is heavy on declarative programming. So I've done a lot of work on declarative programming, and this is where I get most of my examples. I'm not saying that declarative programming will be the next paradigm. Obviously, it's been around for a while, hasn't brought a revolution yet. But I'm saying that whatever it's going to be, some things that we learn from declarative programming will apply. So, very quick rundown, just to give you a taste of what I've done in this space. What's declarative? High-level programming techniques that try to say what we want to compute, but not how we want to compute it. So, a language to be declarative shouldn't have control flow, shouldn't have side effects. So it's more like a specification language, more like a logical language for specifications as opposed to an algorithm for describing, a language for describing algorithms. And what I've done in this space, well, here's the quick summary. I've done a lot of declarative static analysis, probably my primary area of research for the past 10 years, 11 years actually. I've designed some small domain-specific declarative languages. I've been the academic liaison for a company that made its money out of building a declarative language with its backend. And I have also tried to express a lot of other research, for instance, race detection research, in declarative terms. And in slightly more detail, that's basically the top artifact of my research of the past 10 years. Static analysis algorithms expressed declaratively. They analyze Java programs primarily, but also C++ and now Ethereum programs. And we have everything specified as tens of thousands of, or thousands or tens of thousands of logical rules. And it's a very complete modeling of those programs that we analyze. But the entire specification is declarative. And at the same time, I've advised and being the academic liaison for a company, LogicBlocks, that built a language, that built an implementation of the Datalog language, the platform also for my static analysis work, together with a backend for it. And Datalog is a declarative language. You will see it in examples, meaning it's like logic. It's like first-order logic with recursion. And theoretically, it only captures p-time complexity, so you can only express polynomial algorithms, all of them, in Datalog, but in practice, it's a Turing-complete language. But it is declarative. The order of rules or the order of clauses in a rule, and you'll see examples, do not matter for the result of the computation, unlike in Prolog. So the company, for various business reasons, has been successful, so that's a good story. They have been some of the few people who made money out of declarative programming. But the bottom line, and to come back to our story, is that for the past 11 years, my group and I have written lots and lots of declarative rules. Probably the largest Datalog code base out there, and we care very much about efficiency. So everything we write, we try to optimize to make it competitive with handwritten code. We benchmark against competitive frameworks that are written by hand, written using imperative languages. And many times we beat them handily. Other times we just try to max them. So this is even in domains where people had thought that doing this as logic-based rules is kind of inconvenient or even impossible. And there are multiple quotes from people saying, oh, you cannot really expect that this logic-based approach will scale to this or that. And then we did make it scale, and much better than the people who said those things. Yes?
What about code size?
Code size is much more compact than any imperative implementation. So it's very concise. That's the first motivation. That's why we went declarative in the first place. To have very concise specifications of very complex algorithms.
Is it 10x, 100x?
Well, it depends. Sometimes it's not, sometimes it's even going to be more verbose to the extreme. So I cannot give a proof, but on average, for the kinds of things we want to express, the 10x is the least you can expect in terms of benefit. So back to our story now, and you can forget all the declarative part. You don't need it. It just says why I started thinking like this. What will be the principles of next paradigm languages? So here's another interesting quote, which I think is kind of accurate in its generalization. It says, all programming languages nowadays seem very similar to each other. They all have variables and arrays, a few loop constructs and functions, and some arithmetic constants. And indeed, you have to go very far to find a language that does not have loops and functions and things like that. Well, can we get order of magnitude productivity improvements when we're stuck with loops and functions? So, based on this, using this as an excuse, I will state my first principle for what next paradigm languages will look like. And the first principle is that I postulate that productivity and performance will be closely tied. Or, if a language can give orders of magnitude productivity improvements, then its implementation has the potential for orders of magnitude changes in performance. So, both of these are aspects of being abstract. In other words, if you write an algorithm and it's an O of n squared asymptotic complexity, if the language implementation, if the compiler cannot change its asymptotic complexity, maybe make it linear, and in the worst case, make it cubic, but based on the current statistics that it sees, that's never going to happen, then that language, if that language cannot do it, then probably it's not a high productivity language. A high productivity language should be able to have implementations that will bring about devastating differences in performance, is the first thesis here. From now on, I will call the language implementation a compiler. That's a simplification. Maybe we'll not have compilers. Maybe there will be interpreters, specializing interpreters or whatever, but I will call a sophisticated implementation a compiler. So let me...
Can I
yes.
interrupt again?
Yeah.
An example of this is SQL.
An example of this is this, which is effectively SQL. All the examples will be Datalog, which is a generalization of SQL for doing actually useful things and being dependent. So, here's an example. Here's a simple example of something that we write pretty much on every static analysis setting as a Datalog rule. You don't have to follow it very closely. It just says I have an assignment from an actual to a formal between two variables. If I have an invocation side for method, and the formal parameter at a certain index is the formal, and the actual parameter is the actual. Very straightforward, right? So here's the point. The implementation, the compiler, what it will do in Datalog, it will do at least 3 different transformations that change the asymptotic complexity of this code. Whether this code is n cubed or n squared in practice, or linear, will depend on the optimizations that the compiler will affect. So the first optimization is it will do join ordering. That's query optimization. That's what SQL would do. The second will be automatic indexing, adding extra data structures. And the third is incrementalization. So it will automatically incrementalize that problem. So let me illustrate all three of these vastly powerful optimizations one by one. So first optimization, join ordering. This is a rule. Effectively, it's a join. You take all the contents of this big table called GraphEd and you join them with table form or param based on their common variable, which is method, and you join them with all the contents of table actual param based on the common variables with previous, index, and invocation. Who says you have to do it that way? You could do it this way, which is catastrophic. Why is it catastrophic? Think about it intuitively. You have a large program, you're trying to compute all the assignments at call sites of actuals to formals, and you're not even looking at calls. You're just saying, let me try to find all the formal parameters and match them first to all the actual parameters that are at the same position, like the first parameter of a call, and then I will see if there is actually a call to that method that uses that actual parameter. Well, obviously, this is catastrophic. I don't need to give you a proof about the asymptotic complexity. And the engine, the compiler, is supposed to never even consider that join order. In contrast, the other two join orders make some sense. Let's first look at the calls and then match the parameters, the formals and the actuals. Or let's start, maybe most of my methods don't take parameters. So let's start from something that's really small. Let's start from the table that's called formal param. And start from that, iterate over its contents, find the ones that are parameters, the few methods that have parameters, and then go and look at the actual call graph engines. You immediately got an idea of what a powerful language does to change the asymptotic complexity of a program. This is the kind of optimization. And like Will said, SQL. This has been known for decades. This is not new, but think of it in terms of a full-fledged programming language. Similarly, the second big optimization a compiler can effect is data structure selection, or data structure introduction. So in this case here, when we do the join in the order shown, what we actually be doing is we're joining the first table with a projection of the second table when method matches. I would like to have an index that will directly take me to the tuples in the second table that match the methods that I iterate over on the first table. So this means I have a data structure that from method, it takes me to the tuples in the second table. Similarly with the third table. This is data structure introduction for indexing. That's something that a compiler can do automatically in a good declarative language. And my thesis, and you can read more about it in the paper, is that these days data structures are cheap and easy. So next paradigm programming languages will automatically invent data structures for you. There are not many data structures that one needs to hand code. And that's why all scripting languages, they have as a primitive data structure just one map, and they get away with it. Because with one good locality enhancing data structure, like a good B tree, you can get away with almost everything. Sure, you will need occasionally some domain-specific data structures, like cryptographic structures, data structures for big data, whatever. You may need something exotic, but for most programming tasks, you just need a good mapping structure, something with good indexing that also preserves order, and you're done. And the language can invent this for you. And also, what's the space that you waste if you add more data structures? If I have a big table and I index it based on everything, I add 3 more data structures on it. Space is not that expensive, and it's a small space cost. So languages of the future, I expect, will automatically introduce data structures. And finally, the huge gain in declarative languages compared to handwritten code has been so far auto-incrementalization, because this is something that a human cannot do easily by hand. So when in my research we've gotten 10x performance improvements compared to handwritten code, that's the reason. So what's the auto-incrementalization here? If these two relations are recursive with each other, then the join here will be based on the delta, the new elements, the new tuples of this table produced in the last recursive step, in the last step of the recursive iteration. A good compiler for Datalog will do this for me automatically, will implement this delta automatically, will say that I don't need to iterate over all the call graph edges, only the ones that were freshly produced from the very last assign statements that came about. That's really hard to write by hand. We expect a compiler for a next paradigm language to do this. So, based on this principle, which I posit, and you can doubt it or you can question it, I will infer several corollaries. And the first one is that Niklaus Wirth's famous equation that programs equals algorithms and data structures will no longer hold true in next paradigm programming languages. In contrast, what the compiler will do over a program, the output of a compiler when given a program, will be algorithms plus data structures. Future compilers will change the asymptotic complexity of a program. Here's another kind of surprising corollary. Cheapest will be hardest. So, if something is easy in terms of sequential complexity, then it will be very hard to express efficiently in a high productivity language. The examples that I have from declarative programming, all linear time algorithms. Anything that Tarzan has ever come up with that's really clever, depth first, anything that's based on clever use of depth first search, like union find trees, or, sorry, not union find are not on depth first search, but for instance, strongly connected components in linear time, based on depth first search, I cannot do this efficiently in Datalog. So the things that are the cheapest, that we have very clever algorithms to do them very, very fast, yeah, those may be not expressible so easily. Those will need to be hacked. But it's the easy part that may become hard. But anything that's actually harder computationally, it's almost as efficient or more efficient to write in a high productivity language. So my third corollary of the first principle is that, so what? Do asymptotics even matter? Do I care that I cannot express strongly connected components in linear time in Datalog? Most of the time, I don't. Because in a high productivity language, I expect that programmers will often accept suboptimal computations. Suboptimal computations will become dominant. And as a programmer, what am I going to do? Well, obviously, I don't want to use something that's n cubed when I could have a linear algorithm. Or do I? Well, I do if I can limit the scope to something very local. If I can put some restriction and say this n cubed algorithm will only apply in a very local environment, then I don't care about the asymptotics. And there are actually general theorems about that in complexity theory. Any algorithm you take that has a high asymptotic, it's quadratic, cubic, whatever, if you express it as a graph query and you limit the degree of the graph, then suddenly you don't care. It becomes a linear algorithm. So generally, I expect that we will learn to live with suboptimal algorithms, even asymptotically suboptimal, as long as this living with those gives us tremendous expressiveness, tremendous productivity. So here's an example. This is something that I do all the time in Datalog. Pretty much everything I've written in Datalog has some rule like that. And in fact, there are more examples of this flavor in the paper. I just picked the easiest one. And this just says, for all the nodes that precede a node that I will call next, for all the predecessors, pred1 and pred2 of next, I will keep a table here, because it's convenient, that combines both of them. What a waste, right? I'm using all combinations of both predecessors when I can compute them so easily. Do I care that I'm wasting so much effort? Do I care that I have something that's n cubed in size and n cubed in complexity as well? No, I don't. Because it's very, very local. Most of the graphs that I will apply this to have a very limited in degree. Every node will have up to 10 predecessors. I don't care. It's very convenient for me to write this as an intermediate step, so I write it all the time. And so do all my students. Everyone who writes Datalog in my lab writes things like that, and they put a comment on top and say, well, you know, this is inefficient, but it's so local that it will never matter. And the final corollary of the first principle is my thesis that in any high productivity setting, parallelism will be pervasive but implicit. So we will not program parallelism, but it will be there in the execution. The compiler will implement parallelism for us. Everything you saw so far, all the examples that you saw so far, when we execute them, they're executed in a massively parallel fashion. They are joins effectively, joins of tables. So we just partition, the table is automatically partitioned, and any number of threads can operate on the partitions and then join the results. So I don't think that in the future we are likely to have high productivity languages that will use anything like threads or explicit synchronization, but even going further, I don't even think that they will even use Erlang-like constructs, because I see Costis over there. Anything that expresses parallelism at the level of the programming model will not even be there. Parallelism will be hidden, is the thesis. And with this, I'll move to the second section of a second principle, let's say, which is the changes that I expect will come about in the semantic invariance that the language offers. So, principle number 2 that I will postulate says that any high productivity language will need to offer strong semantic guarantees. So we'll need to give some guarantees about what code can do and how new code can affect old code. So this looks too abstract right now, and I know, and I would object to this statement if it was put in front of me, but you will see what I mean in a second. So the support for this is obviously that we want something high productivity, which means we program at a very high level of abstraction, but an abstract specification means that it's too easy to break things. And that's an everyday experience for us. It's not just a rare occasion. We make one word changes, and either the complexity of our algorithm or its correctness change drastically. So we need language design that will very naturally keep the programmer's sanity. So what do I mean? Let's make this a little more grounded. In Datalog, in the area where I'm experienced, the number one sanity-preserving feature is monotonicity. When I write a new rule, primarily it cannot take back inferences that have been produced by previous rules. So I build towards a goal. I get successively closer to a goal. Now, that's not entirely true, but it's close enough. I can violate monotonicity. There are syntactic constructs to violate monotonicity in specific stages of computation. I need that pretty regularly, but I know when I do it. Primarily, everything is monotonic. If something used to hold, adding more code does not break it. The second sanity-preserving feature is terminations. Termination. Programs will convert. Again, that's not entirely true. I can very quickly make mistakes that will bring non-termination. But it's close enough. If I stay in the disciplined fragment of Datalog, I know that I have no non-termination problems. If I use constructors, I know that I have potential termination problems. So I think about what I'm constructing a lot more closely than anything else in my specification. Okay, so I'm postulating some principles here.
Can I maybe comment? I think that's related to this idea of having some performance model. The language has to give you a performance model that you can be comfortable with. Making some small change isn't going to make it, run super slow.
Yeah. Can everyone hear what Will is saying? In the back? No. Okay, let's have the question with the mic.
So, I just said, I've heard before that languages need to have a performance model that you can be comfortable with as a programmer.
Yeah.
And that's an essential aspect of it.
Yeah. So I'm going a little looser than that. Given that we still don't have good performance models that, for instance, account for locality, we still don't reason very well about anything that doesn't have random access memory. I don't want to go as far as say we need the performance model, but we need a sanity model, and these are so crude as to be rather sanity models rather than performance models. When we say monotonicity or non-termination, they're much cruder than saying, well, you have a programming model, you have a model in your head about the performance. So yes, performance, but to the extreme. So the next question that you may ask before we go to the very last set of principles is, okay, but you're telling us some things here about principles of next generation languages, but we already have good principles for this generation of languages. Where do these go? Do we throw them out the window? So we have lots of good principles, right? We know things that make a successful high-level language already. The first is what I would call a module abstraction. Everything that Guy Steele has described in his Growing a Language paper. Fantastic principle. We need to be able to package reusable functionality in a reusable, parameterizable, ideally, module. Here's another good principle. Let's add to that syntactic configurability and we get language extensibility. That's also a good thing. We want that in our languages. People want that. How about the base definition of modularity, which is hiding? The ability to take part of the code and hide it and only access it through an API. And how about interoperability or multi-paradigm programming? Use the right tool for the job. Program one part of my application in one language or one paradigm and use another paradigm for a different part. All of those are great principles, right? I mean, we know them, we love them. Are they enough to bring us to next generation languages? So, my first thesis is that these are not enough. They cannot get us to the next paradigm. And in fact, they may not even appear when the first next paradigm languages come about. So, these are great features, but they address what Brooks would call accidental complexity and not essential. Who cares about modules when I can do in 100 lines of code what someone else would need 10,000 lines of code to do? When we get to next paradigm languages, the principles that we now know are valuable may be second-order effects. Well, not quite all of them. I think the multi-paradigm part, or interoperability, will be essential. So I expect that the very first next paradigm languages will at least give you a way to hack in some imperative code, because remember, we said, I cannot do strongly connected components efficiently. That's Corollary 1, 2. The easiest computation will be hard. So I expect some interoperability features. But I don't necessarily expect in the first incarnation of next paradigm languages to see features that have to do with data hiding or with growing a language kinds of module abstraction. And this brings us back to the Brooks terminology. The no silver bullet argument that all progress in programming languages addresses accidental complexity instead of essential is now kind of turned on its head. Because the kinds of things that I expect will bring next paradigm languages about are the things that address exactly essential complexity. Program synthesis, declarative reasoning, machine learning, all sorts of statistical inferences, they actually do address the core difficulty of programming, not just the accidental complexity, which makes the problem inverted. Because if the essential complexity is addressed, then maybe the accidental complexity will become the bottleneck. There is a diminishing returns argument. Let's say I have the core logic of a complex application take up 70% of the programming effort. Well, even if I make it 10x more efficient, well, the other 30%, the accidental complexity, stays there, so the overall benefit is just 2.7x, and you can compute it. Tell me if I'm wrong. So perhaps accidental complexity is an argument against next paradigm languages ever appearing. But I actually think that all these good language principles that we just discussed are great for addressing this. Also, in many cases, I expect that the simpler tasks, the accidental complexity, will parallelize better. Think like you're managing a large software project. What's easier to add manpower to? The UI or the core logic? The core logic is very hard. You need experts, and the experts have to make changes kind of sequentially. Every change depends on every other. They are deeply mutually recursive. Whereas the UI, you can have 5 people work on it, and they will not be 5x efficient, but they will certainly be more efficient, much more efficient than one person. So with that, I will postulate a bit about the impact that next paradigm languages will have on our everyday work, on development workflows. And maybe I should speed up. Oh, I have 5 minutes. If I have 5 minutes, I'm great. Okay, I like this quote by Jan Willem Maassen. It's actually a quote describing a whole paper on machine learning and the kinds of differences it makes, the kinds of difference it makes for everyday programming systems that use machine learning. And he says, we have programs that are vastly powerful but also vastly mysterious. Meaning small changes can badly destabilize the system, and we don't yet know how to talk about debugging or maintenance. And that's exactly my last principle, pretty much. So principle 3 is that our programming workflows will change, and majorly so. Next paradigm languages will disrupt all the well-established patterns we have. Because high-level code will be so much more terse, we will have severe impact in testing processes, in whether we need formal verification, in how we debug, the mental burden that we have. And let me try to elaborate a tiny bit. So, this may not seem like a big deal, so here I definitely have to appeal to my experience. The number one thing that has been different for me in the past 10 years that I've been programming mostly in Datalog versus before when I was mostly programming in C++ and in Java has been the incrementality of my development. So now I can pick up from where I left off 2 weeks ago with a very low mental burden. Because everything is so much more concise, and I have this trust that I'm only building monotonically on my previous specification. So I think this will be one of the most striking observations. In next paradigm languages, it will be much easier to develop programs incrementally. What else will change? Testing. If you write something that's very high level, you're likely to spend more time testing than actually writing code. There's not that much code to write in the first place. So you will spend a lot of time trying to confirm that what you wrote made sense. And testing can also be very complicated. It can be deep and involved. And debugging is very hard. Debugging is always hard when you have something whose intermediate results are much more numerous than its final results. When you collapse all intermediate values, debugging is insanely hard. So here's a kind of trivial example. I have the simplest recursive computation, a transitive closure over edges to compute paths. Even in this, just saying there's a path from source to target when there's a path from intern to target and between source and intern. Intern is dropped in the final result. Well, can I keep it around just for debugging purposes? Many times you cannot. This would blow up the size of your relations by one more element. You have a table, now you make it 1,000 times bigger. Can you afford that? Maybe not. So debugging can be really hard. And it has to also be expressed in high-level terms. So will testing. And what I will finally postulate is that in high-productivity languages, in next paradigm languages, there will be a different balance of formal reasoning, which is kind of obvious, but I think we need to state it concisely. I think formal proofs will be easier yet they will also be less necessary because a large part of formal proofs is the formal specification. It's specifying the behavior in a formal notation, which in higher productivity languages will be the same effectively as coding. A specification plus a little bit more will be the code. So with this, I will lead to my conclusion. So my concluding thoughts, first of all, are to invite discussion. This is just a view from where I stand. This is why this is an essay. I'm standing at a particular point in the research space. This is how I see the future. You stand at different points. You probably see the future differently. So as a community, we should have a discussion about next paradigm languages. Are they feasible? And what will they